a lot of people out today for sports. I don't want them to miss stuff. If they miss stuff, now they won't miss stuff. Okay, so at this point, we've learned two equations that are very similar. Equation number one, Newton's second law tells us that the net force acting on an object can be calculated by multiplying the mass of the object by the acceleration of the object. And more recently, we have learned that you can calculate weight, the definition for which is force of gravity, that you can calculate that by taking the mass of the object and multiplying it by the acceleration of gravity. All right, so to be clear, both of these equations are mass times acceleration, but they're not. Only the top one is mass times acceleration. The bottom one is mass times acceleration of gravity. So what the bleep do I mean? Here's what I mean. This A represents the actual acceleration of the object as determined by its motion. So if we're talking about that little orange duck that's sitting there, that has an acceleration of 0. Okay? If we're talking about this cart rolling down the ramp, that has an acceleration that's somewhere between 0 and 9.8. Follow? So this represents the actual acceleration of the object. Does that make sense? All right. Similarly, or well, maybe not similarly, this is that little g there stands for gravity. So that is the acceleration that would be produced by gravity if it was the only force on the thing, which on Earth is always negative 9.8 meters per second squared. So this duck has an acceleration, A equals 0. But it has an acceleration of gravity of negative 9.8 meters per second squared, even though he's not falling. Does that make sense? Okay, cool, because I sometimes see people get those tangled up. All right, so that was general thing number one. That is also not how you spell actual, as a side note. There's only one L in actual. Yes.
On your answer key, you were showing the word for acceleration of gravity. Do we have to do that, or can we just say it's negative 9.8?
Are you talking problems 13 and 14?
Yeah, I think so.
Yes. I did that for a specific reason, and I'll go over it in a minute, so hang tight. But in general, no, you don't need to show it. Yeah, you just know it. But I did it on those problems because I was trying to make a point, which I'll talk about here in a minute. Okay, so is everybody good with everything here except for my spelling of the word actual? Okay, cool. Thing number two. Well, maybe this isn't even thing number two. So what's this? Force of gravity is also known as weight. So from now on, any time in my class that you hear the word weight, I want you to think, oh, that's the same as force of gravity. They're literally synonymous. Okay? Units. Mass will always be in kilograms. Weight in this class will always be in newtons because we use the metric system. Okay? Those people in Europe that give you their weight in kilograms are lying. That's not their weight, that's their mass. Cool? All right. Which way does gravity pull stuff? Down. And as a result, your force of gravity will always, in this class, be negative. So on problem number 12, where it says find the mass of a 600 Newton student, what's going on there is, here's your student, all right? He is a 600 Newton student. So what am I telling you when I tell you that 600 Newtons? That's his weight. That's the force of gravity, right? Like if I said a 150-pound student, you'd be like, oh, 150 pounds, that's his weight, right? And newtons and pounds measure the same thing. So a 600 Newton student, that's his force of gravity. But remember, that force of gravity pulls the student down with a force of 600 newtons. So when you calculate mass, it's negative 600 newtons equals mass times negative 9.8 meters per second squared. And I point all this out because the negatives will cancel, resulting in a mass that is positive whatever it is, 61 kilograms or whatever it is. Cool? You can't have a negative mass because you can't be made up of a negative amount of matter. Cool? All right. Those were the general things I wanted to talk about. Does anybody have any other questions on 1 through 12? I don't know why I did this with my arms, but I'm going to do it again. Okay. I would like to talk about 13 and 14 real quick because there's a point to it. Are you prepared to hear the point? Here's the point. Numbers 13 and 14 deal with bowling balls that are being dropped. In number 13, the ball has a mass of 4 kilograms, and it asks you to make a free body diagram, find the net force, and find the acceleration. Cool. And then you got to 14, and it was the same stupid thing again. Why the hell did you do that to me? After I already know how to do it, so I just did it at 13. Wasn't that hard the first time? Why are you making me do it twice? Well, 15 was hoping or trying to make sure that you made the connection between what I was trying to show you with 13 and 14. So I want to make sure you guys get that. So here's what I was trying to get at. Check it out. 4 kilogram ball. We drop it off a building. No air resistance or anything, so free fall. What forces are on it? Gravity. Gravity's pulling this thing down. So let's see, we can calculate the gravity by doing 4 times negative 9.8, and it gives you negative 39.2 newtons. Okay, well that means that our net force is going to be negative 39.2, right? Because it's the total of all the forces. There's only one force. Net force, negative 39.2 newtons. All right, so that's parts A and B for number 13. Yes? All right, number 14 was almost the exact same thing, except the ball was bigger. 8 kilograms of ball. Here we go. Gravity's pulling this thing down with a force of 8 times negative 9.8 is 78.4 newtons, which means that the net force on this guy is going to be negative 78.4 newtons. Yes? Okay, so that was part A and B. Part C says find the acceleration. So if I take these 2 bowling balls to the top of the Empire State Building and suck all of the air out of Earth, and then drop the bowling balls off the tower, which one's going to fall faster? Good, thank you. All my other classes were like, the heavy one. No. No. That was the whole point of the paper and book demo that we did 4 weeks ago, right? It was the whole point of the British dude talking about the vacuum chamber with the bowling ball and the feather, right? Everybody know what I'm talking about? Everything falls at negative 9.8 meters a second squared, right? But a lot of people in my other classes were like, the heavy one falls faster. There's more force on it. That makes sense. There's more force on it. It seems like it should fall faster, right? But it doesn't. Why? Well, let's see if we can figure out why. All right, so let's do this. Let's calculate the acceleration for the ball at number 13. Acceleration is net force over mass. So for the ball in number 13, the net force is negative 39.2 newtons. And that force is accelerating a mass of 4 kilograms. And so when you divide it out, you get negative 9.8 meters per second squared. I know this logic is a little circular, but bear with me. Everybody good with that? All right. Over here, this ball's way heavier. There's way more force on it. So when I calculate its acceleration, it seems like I should get a bigger value, right? Because now instead of having 39 newtons, I've got like 78 newtons. But, what? What do you got here? Mass, right? So why is this not going to result in a bigger acceleration? You got more force, but you've also got more mass. Which bowling ball is harder to move? The big one. And so it takes more force to give it this same acceleration because it's got more mass. So this is twice as much force acting on twice as much mass, but you still get the same acceleration. Does that make sense, you guys? All right. So why does the bowling ball fall just as fast? It's got more force on it, but it also has more mass. Cool? Ryan, does that make sense? Everybody, does that make sense? Is anybody confused, confuzzled, conflagrated? Is that a word? I think it is a word, but it doesn't mean confused. All right, everybody happy? Awesome. All right. Number 16 was about air resistance. I didn't give you guys notes on air resistance because I wanted you to try some problems on it. So let's make sure that you got out of that what you were supposed to. There are two big ideas that you need to get out of number 16, which is the problem about air resistance. So we should talk through that. I just spilled coffee all over Ethan's desk. Don't tell him. Make sure he doesn't watch this video. All right. 16. All right, so I'm going to tell you some things about air resistance that you probably already know, even if you don't know that you know them. So here are the things that you know. How much air resistance is on an object depends really on two main things. It depends on sort of the shape of the object. Okay, that is why when we did that book and paper example, the first time I dropped the paper, it kind of floated like this, right? Because it has a large surface area and thus had a lot of air to push, right? But just by changing the shape of the paper, I can change how the air resistance affects it, right? Okay, so air resistance depends partly on the shape, size, surface area of the object, okay? Secondly, and the piece that is more important, it turns out that how much air resistance acts on an object depends on how fast it is going. Okay, you should write this down. The faster an object is moving, I will even write it down. Here, look. You should write this down. The faster an object moves, comma, the more force air resistance exerts. Faster an object is moving, the more force air resistance will exert on the object. And like I said, you know this. Because when you walk down the hallway at school, you don't go, oh my God, the air is totally messing up my hair. Okay? But if you drive down the street on a moped, now you're worried about the air messing up your hair, right? If you put your hand out the window of your car while you're driving down Fisher, no big deal. But if you put your hand out the window while you're driving down the freeway, it's like, right? Because the faster you're going, the more air your hand has to push per second, right? Okay, here's a real simple example of that. Look, here's a piece of paper, right? It has my name on it. Okay, if I walk this way slowly, watch what the paper does. Nothing, it just hangs still, right? Because I'm not pushing that much air per second with the paper. Whereas if I go back here and do the same thing, but this time I move very quickly, it moves the paper, right? Because I'm pushing more air per second, that means the air pushes the paper and causes it to tip back like that. Cool? So, the faster you go, the more air resistance there is. Good? All right, great. So, when you jump out of an airplane, as you fall, you go faster, right? So your air resistance is going to change. Okay? That's what number 16 is about. Okay? So, did anybody have any problems calculating the accelerations through that problem? It's just net force equals net force, right? In each problem, you know your gravity is, I think, negative 784, right? Just 80 times 9.8. And then you're given your air resistance, so you can find your net force and find your acceleration, right? Okay, so I'm going to run through the answers to that problem without doing the calculations, unless anybody has objections. But let me talk about the concepts that you were supposed to get out of that. Okay, so here's the deal. So for 16A, Roy has just jumped out of the airplane. So here he is. Here's Roy. He's got a mass of 80 kilograms. He's not moving yet, so there's no air resistance. Gravity's pulling him down with a force of negative 784 newtons. Since there's no air resistance, his acceleration is going to be the acceleration of gravity, negative 9.8 meters per second squared, right? Everybody good with that? Since gravity's pulling him down, he's going to speed up, right? He's going to go down faster and faster and faster, right? So at some point later on, part B says after 3 seconds, here's Roy again, he's still 80 kilograms. Gravity's still pulling him down with the same 784 newtons, but now there's an air resistance of 144 newtons. So now there's less downward net force, right? That means there's going to be less downward acceleration. And so if you do net force equals net force, you'll find out that the acceleration is negative 8 meters a second squared at this point. Cool? Right? And at this point, he was moving down. I think the arbitrary number that I picked was 27 meters a second. But whatever, he's moving down. That's important, right? Now, he's still going to gain downward speed, just not as quickly as before, right? But the important thing I want you to notice is because of this, he's going to speed up. He's going to speed up. And as you speed up, what happens? More air resistance, right? So when you get to part C over here, more time has elapsed. He's still 80 kilograms, but now he's moving down at 50 meters a second because he was speeding up before, right? So now you've got your gravity, you've got your air resistance, and I think in part C I made the air resistance, what did I make it, 384? Yeah. Notice the air resistance from here to here got bigger, right? Because he sped up. Okay? But now what happens is your net force is less, and so your acceleration is less. Now it's only negative 5 instead of negative 8. Ignoring the signs, it's less. But he's accelerated more slowly. Good? Do you guys agree he's still going to speed up, though? Yeah, he's still going to speed up because gravity's still winning, right? So what that means is by the time you get to part D, gravity's still pulling down with negative 784. Air resistance is very big now because he's had all this time to speed up. It's 720. The acceleration, if you figure it out, is negative 0.8. But the point is, he's still speeding up. And as he goes faster and faster and faster, the air resistance gets bigger and 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 bigger until something important happens. Well, assuming it doesn't hit the ground, that would be important. Let's assume he hasn't hit the ground yet. So yeah, what do you got, Hannah?
Until the force, the air resistance force is larger.
We'll talk about larger in a second, but equal to is what we're worried about, okay? Because he's going to keep speeding up. Eventually, it's got to get to 784, right? Okay? So for part E, and I'm not ignoring you, those of you who had your hands up, so give me one more second. So in part E, what happens is this. So here's Roy. He's moving down really fast. I think it's 55 meters a second, according to the problem. Your gravity's still negative 784 newtons. But now he's moving so fast that the force of air resistance is also 784 newtons. So why is that important? What happens now?
Net forces can also acceleration.
Perfect, yeah. The forces cancel out. So now my net force is 0. That means my acceleration is 0. Does that mean he stops falling? Does it mean he stops moving? No, it means he stops accelerating. So now his velocity terminates. It stops increasing. Okay? And it becomes constant. The velocity at which this occurs is called terminal velocity. Okay? So, once the object, you should write this down. This is the other thing you need to know. Once the object is moving fast enough, oops. Once the object is moving fast enough, the force of gravity will be canceled. by the force of air resistance. So your net force is 0 and acceleration is 0. Oh, rat, I wish I had, oh, here. Oh, whatever. The velocity at which this occurs is called terminal velocity. Yes, Hannah.
So if there is no air resistance at all, then there would be no terminal velocity.
That's correct, yeah, because you would just keep speeding up indefinitely, right? So there'd be nothing working against gravity. Very, very good. All right, other questions about this? Did I lose anybody there in that train of thought? There's a lot going on there. This is one of the few times this year. There's only 2 types of forces we talk about this year where the force is not constant. Air resistance is one of them, and then later on when we get to springs, the force of a spring is not constant. All right, any problems with what's up there? All right, now, here's a thing that I didn't tell you on the homework. Are you ready? Are you excited? You're gonna be excited. Roy is really smart. He brought a parachute. Seems like that should do something, right? I wonder what that parachute will do. So let's see. So right now he's falling like this, right? Right? Gaining speed, gaining speed. Eventually he hits a terminal velocity of about 55 meters a second, right? All right. Then he's like, oh, bleep, here comes the ground. I'm going to hit it. Poof, he pulls his parachute. What the parachute does is it, poof, opens up, right? And so he's moving very fast, but now because the surface area is bigger, what's it going to do? It's going to catch more air, producing more air resistance, right? Okay, so watch what happens. This is neat. So here's Roy. Hello. All right, so gravity's pulling him down. Oh, wait, no, I'm sorry, I did this wrong. Here's Roy. Ah! Gravity is pulling him down with a force of negative 784 newtons. And he realizes that the ground is quickly approaching him, so poof, he pulls the parachute. All right? And the point is, the parachute is shaped like this, right? Like an umbrella, right? It catches all the air. And so the idea is, right now, he's moving down at 55 meters a second. And because that parachute catches so much air, it produces, poof, a huge amount of air resistance. All right, so I'm going to choose an arbitrary number. Oh, really? You again, huh? Mr. Keyboard, my arch nemesis. All right. That says 1,000. All right, so you've got 1,000 newtons now. Okay, so let's think now about what's happening. He's moving down, right? He just fell out of an airplane. He's moving down really fast. Poof, parachute. The parachute produces an upward force that's bigger than the downward force. So does that mean he goes up? No, it doesn't. Despite what Hollywood has led you to believe. When you pull a parachute, you do not go up. But it looks like you do in movies. Here's why. All right, here's Vin Diesel. He's just jumped out of an airplane. He's going to save the world, right? So he's falling, right? But we're able to watch him on the movie screen. That's because there are actually 2 people falling. There's Vin Diesel falling, and there's a cameraman falling together, right? This guy's videoing Vin Diesel falling, right? Okay. Then Vin Diesel's like, oh no, here comes the ground, and he pulls the parachute, right? So right now they're both moving down at 55 miles an hour. He pulls the parachute. What does the parachute make him do? Slow down. Did the cameraman slow down? which he hasn't yet because then the camera would get shaky. Right? So they're both falling. They're falling at 55 miles an hour or whatever it is, 55 meters a second. Poof! The cameraman keeps falling. Vin Diesel keeps falling, but just slower than he was before. So relative to the camera, Vin Diesel's going up. Relative to the ground, he's still going down really fast. Just not as fast. Make sense? And
Isn't the air resistance on the parachute so wouldn't use, like, even though the parachute?
but he's tied to the parachute, right?
Whether it's possible that you go with the parachute, so you.
Say that one more time.
Well, because I kind of like the whole car thing, how he's not attached to the, or he's not the car.
Right, the parachute and the, yeah.
Wouldn't that just affect the parachute?
Well, but I mean, so I guess I am oversimplifying things in that I'm assuming that the parachute and the dude move together because they're tied together, right? He certainly can't be moving down any faster than the parachute, right? Because the rope is only so long. And once he gets to the end of the parachute rope, that's it, right? And so what's happening is the parachute is above him, pulling him up, resisting his downward motion, and he's tied in by the ropes. So it's safe to treat it as one object. But I like that you're thinking that because that's important that you think about, like, is this force really on this object? So good job. All right, so does everybody see? All right, so what did we just say the effect of the parachute was? What's it going to make him do? Slow down. He just slowed down. So what's going to happen? Air resistance is going to get less. So right now, he's going down at 55 meters a second. Poof, parachute. This parachute causes him to slow down. When he slows down, now he's going down at slower than 55. That means the air resistance decreases. But air resistance is still winning, so he's going to slow down some more. As he slows down more, the force of air resistance gets less. Air resistance is still winning, he's going to slow down more. Until eventually, you get back to terminal velocity, right? But it's a different terminal velocity now, right? Because we had to slow down to get back to that point because the parachute catches more air. Does that make sense, you guys? A lot going on there. All right. Here are the things you need to know. Faster you go, more air resistance there is. When you reach the point at which your air resistance cancels out your gravity, the velocity at which that occurs is called terminal velocity. Cool? Cool. Any questions? Cool. Thank you for your patience. I know that was a lot, and I believe important. Okay. So you guys watched the 3.5 video last night. I want to give you guys some time to work. Unfortunately, you're already not going to have as much time as I hoped. I wanted to do a quick demo about normal force. Maybe I'll wait and do it tomorrow when more people are here. How many of you are out tomorrow for outside? Friday. Okay. Let's hold off on the demos. So here is the only thing that I want to say then, and then I'll let you guys get started. This is, did I say this at the beginning of the hour? I said this in one of my classes. This, the 3.5 stuff is where this material starts getting tough. Did I say this yet to you guys? Like you watch the video and it's like, oh, this seems easy, but then you try it on your own and stuff. So take the problem slowly. All of the problems revolve around net force equals net force. So process is always the same. Start with the force of gravity, always. Okay, so that's going to be this, right? Then, any forces that you know. Maybe it tells you the force of Roy and the force of Sally. Okay? Then, ask yourself, do I know the acceleration? Oftentimes, it's 0. So watch out for that. And then solve for the thing you don't know. Maybe you got to find the acceleration. Maybe you need to find the force of friction. Okay? If there are both horizontal and vertical forces, because this is a first-year course, either all of your horizontal forces or all of your vertical forces will cancel. Does that make sense? Okay, so either your net force will be horizontal or your net force will be vertical. Okay. When you're looking at your vertical forces, deal with your normal force last. Okay. I'll talk more about normal force tomorrow. If you, I don't think you guys need to remind me because they'll come in and you'll be like, I don't understand normal force because that's what always happens. But do normal force last. Like it's the last one of the vertical forces that you want to try to figure out because usually it's the thing you don't know. It is often equal to the force of gravity, but not always. Here's the real quick summary of what normal force does. I said this at the very end of last year. Somebody was like, why didn't you say that at the beginning of the year? And I was like, it never occurred to me. So here it is. So normal force will always exert. Well, so what is normal force, you guys? Where does it come from? Inanimate object or inanimate surface that the object is in contact with, right? So the reason that the duck is not falling now is because there's a normal force from the track pushing them up, right? And the reason that my calculator right now is not going through the smartboard is because there's a normal force from the smartboard pushing the other way, right? So the force of me pushing the calculator is canceled by the force of the smartboard pushing the calculator, right? And the normal force will always be exactly strong enough to prevent the object, in this case the calculator, from going through the surface. Does that make sense? So that's how you figure out how big your normal force has to be. It's exactly big enough to prevent the object from going through the surface. No bigger, no smaller. Good? Okay, cool. Try the homework. We will talk tomorrow. Tentatively tomorrow, I want to do a target check. We'll have to see how we're doing on time and comprehension.